Okay, so now that we have thoroughly discussed a whole bunch of tests for convergence of a series, now we're actually going to start getting into applications of the series. So recall, as I mentioned a while ago in the section on sequences, the whole point of doing this discussion in the first place is to be able to talk about Taylor series. Taylor series being one of the most ubiquitous mathematical techniques in science, and certainly the most important thing to learn in calculus too. So the method of Taylor series involves taking a given function and replacing it with a polynomial approximation. And that polynomial approximation is going to be a partial sum of this series. Okay? So given a function, we have the associated Taylor series, where this parentheses n indicates derivatives. So each term of the series has a higher order derivative. And this approximation is going to be valid for values of x near to the point a. So if you're only interested in values of the function close to, say, x equals 5, you would compute the Taylor series for a equals 5, and then maybe take like the first 5 terms of that. Now, clearly this is a series, so our study of series up to this point is at least justified in that regard. But this isn't quite a series like we've seen before. Notice that this guy has 2 variables in it. It has n. Well, okay, n is the index of the sum, so that's no surprise. It has a. Okay, well, a is a constant that's decided beforehand, so that's not really a variable. But then it also has this x. So x, in this case, is in fact another variable. And the interpretation of this expression here is as a function. Namely, a function where you input a number x, and the output is a series. So for instance, say for instance that we were looking at the function f equals the exponential function with base 2. So if we wanted to compute the Taylor series for this guy, we would have to figure out what the nth derivative is in general. So for exponential functions, that's easy. Every time we differentiate it, another factor of natural log 2 pops out. So the nth derivative is just natural log 2 to the nth power times 2 to the a. So if we take the Taylor series with a equals 0 and x equals 1, well, let's see, 1 minus 0 is 1, so all of these terms just end up being 1. 2 to the 0 is 1, so similarly that disappears. So we obtain this series here. So we are interpreting this as the output of a function. So the input to the function was x equals 1. The output to the function was a series. And indeed, this is a series that we're more or less familiar with, because now it only has the one variable, namely the index of the sum. So that's how we're interpreting this dude. We're interpreting it as a function. You feed it an x, and it outputs a series. And you can show that this guy converges using the ratio test. So, this section is going to be all about this idea of defining functions with infinite series. Defining functions where the input is a real number and the output is a convergent series. So of course there's a lot of ways that we could possibly approach this topic. What we are going to do is we are going to look at functions, so-called series-valued functions, that have a very, very particular form. So, a power series centered at a is a function of x which takes the following form. So x is the input, and this series is the output. Okay? So it's a function that gives you series. In other words, it's this dude, right? I'm just writing this out so you can see more clearly the pattern here. So these C's are just some sequence, and this A is some number. So the sequence C sub n and the center point A, those are the data of the power series. A power series is uniquely determined by that sequence and that center point. X is the independent variable, and because this is a function, it makes sense to talk about the domain. So the domain of this is the collection of numbers x for which this series converges. Okay, so let's apply the ratio test to this thing. That's going to give us some insight as to when power series converge. And we're going to get a very nice result out of this. So recall, when we're doing the ratio test, we take the limit of the ratio of subsequent terms. So we take the n plus 1th term divided by the nth term. Now, you can clearly see that a whole bunch of these x minus a's are going to cancel, so there's only going to be one x minus a left over. Take absolute values, and then x minus a doesn't depend on n at all, so we can pull it out of the limit, as we've done. And the only thing that remains is the ratio of subsequent terms of the sequence associated with the power series. So since this is the ratio test, if this quantity is less than 1, then the series is absolutely convergent, and it follows that this value of x is in the domain. So that's what I write here. Now there are a few cases to consider here because x is a variable. X is not fixed. So suppose, for instance, that x is equal to a. So x is at the center point. Well, if x is equal to a, then x minus a is equal to 0. So this inequality becomes 0 less than 1. Well, of course, that's true. So that means that this value is in the domain. Because it gives you because it gives you a true inequality. So suppose that x is not equal to a. Well, if this limit is equal to 0, well then once again we end up with the inequality 0 less than 1, which is always true. So if this limit is equal to 0, then that means all x's are inside the domain. It doesn't matter what value of x you plug in here, we're always going to end up with the inequality 0 less than 1, which is true. And hence the series will always be absolutely convergent. On the other hand, if this limit is infinity, well then the inequality becomes infinity less than 1, which is never true. So in that case, the only value of x which is going to work is x equals a. For literally any other value of x, you get this inequality, which is false. So if this is the case, then the domain consists of only one point. If this is the case, then the domain consists of all real numbers. So what if this limit is neither 0 nor infinity? So what if this limit is just some number? Well then, we can divide both sides by that limit to get absolute value x minus a is less than that. So notice the difference. Instead of c sub n plus 1 over cn, it is now cn over c sub n plus 1. The fraction flipped upside down. That's because I took the reciprocal. So, if x satisfies this inequality, then that means x is in the domain. Conversely, if this limit L is larger than 1, then by the ratio test we know the series is going to diverge, and so we get the same result just with the inequality reversed. So if x minus a is greater than that, then x is not in the domain, because then the series is going to diverge. So we summarize these results. The stuff in the box is what the real takeaway from this is. So you're given a power series, and suppose that the associated sequence is it never takes on the value 0. Well then, we can define this quantity, and that's going to be called the radius of convergence. So notice this quantity is the same one from up here. And why did I have to say that the CNs are not 0? Well, because if the CNs are ever 0, then we end up dividing by 0 here, which is a no-no. Okay, so here's the possibilities. If this dude is equal to 0, well, then that is the same as saying that the reciprocal is equal to infinity, right? So if there's So if this dude was infinity, that was the case where the domain was 1 point. So if this dude is 0, then that means the domain only consists of 1 point, namely x equals the center point. If this dude is infinity, well, that corresponds to the case where the reciprocal was 0. So in that case, all real numbers were in the domain. Okay? So if this guy's infinity, then the series always converges, no matter what value of x you plug in. If r is something else, so r is just an ordinary finite non-zero number, well, then we get this situation. So it converges if absolute value x minus a is less than r, and diverges if it's greater than r. So if you recall what this sort of statement actually means, this means that if x is inside this interval, then it converges, and if it's outside this interval, then it diverges. Right? Because absolute value x minus a is the distance between x and a on the real number line. So draw a picture, you can see that this is exactly the same as saying that x is in that interval. That's algebra 1 stuff. I don't want to go into too much detail there. So one thing that I do need to mention, though, is that in this case, we know that the series converges for values of x inside this interval and diverges outside, but we actually don't know anything about the endpoints. So if x is equal to a plus r or a minus r, then we actually just have to plug in the value of x into the power series and just see what happens. And that's because when x is equal to a plus minus r, the limit in the ratio test actually ends up being 1. So we need to use a different test. So I hope all of this will become clear when we start doing the examples. But yeah, the thing to take from this is that the domain of a power series is either a single point, the whole line, or a finite interval. And you can now see why this number a is called the center point, because the interval is centered at a. Incidentally, the domain of a power series, being an interval, is called the interval of convergence. And the radius of this interval is r, which is why this dude is called the radius of convergence. And you can sort of think of these as being limiting cases. So if the radius is 0, then the interval is just a single point. And if the radius is infinite, then the interval takes up the entire line. So radius of convergence is an evocative term for this. Okay, so nothing else to do but to do a whole bunch of examples. Because ultimately what we're doing is we're just computing the radius of convergence and then drawing our conclusions. However, we do still have to check the endpoints, so it's a good thing we have all of these tests under our belt at this point. Okay, so first off, for what values of x is this series convergent? So it's just asking us to find the domain. Well, we need to know what the sequence is, and we need to know what the center point is. Well, that's, I think, pretty clear to see just from the form. So the sequence is just given by the sequence of factorials. Notice that the starting point is at 0. For power series, the starting point is always going to be 0 by convention. Well, not always, but well, you'll see. Actually, yes, always. For a power series, it does have to start at 0. Okay, So that's the sequence, just the sequence of factorials. And the center point is a equals 0, right? Because x minus a to the power n, well, here the minus a doesn't show up, so this is like you're taking x minus 0 to the power n. So let's compute. Okay, well, before we go ahead and do this, we do need to make sure that the sequence never becomes 0. And that's true. The factorial is never 0. So we're good. We can proceed. So you might be asking, well, what happens if the sequence does include zeros? Well, we'll get to that. In that case, you'll just have to do the ratio test directly. This formula won't work. But anyway, we're not there yet. So let's go ahead and compute the radius of convergence and draw our conclusions from that. So that's Cn over Cn plus 1, and the order is important. The n plus 1 has to be on the bottom. If you get them reversed, then you'll end up with the wrong conclusion. So here, these are just factorials. Factorials are always positive, so the absolute value isn't going to do anything for us. Like so. Okay, well, let's use our trick with factorials to cancel a bunch of stuff. Because n plus 1 factorial is the same as n plus 1 times n factorial. So then those n factorials cancel. So we just get that. And in the limit as n goes to infinity, that is 0. Okay. So the radius of convergence is 0. That means that the series converges at only one point, namely the center point. And here the center point was 0. Incidentally, if we were to just plug in x equals 0, then every single term of the series is 0. So it's like we're just adding up infinitely many zeros. So indeed, it does converge in that case, but that's sort of trivial. Okay, what about this dude? Now, there's a little bit of a technical issue that we need to discuss. So the starting point here is n equals 1. But for power series, the starting point has to be n equals 0. So the reason that's important is because it's going to indicate what the sequence is. And you need to know the sequence accurately because that goes into the computation of the radius of convergence. And we also need to know that it's non-zero eventually. So to get a better idea of that, let's actually write out the first few terms. So this is... So n equals 1 is the first one. Then n equals 2. Then n equals 3. Okay, and from here on out, it is, well, you can clearly see the pattern. So notice that in a power series, the first term is a constant, and the second term is the one where x shows up. So that means this guy here is actually the second term of the power series, and the first term is 0. So the sequence associated with this power series is has to start with 0. and then 1, and then 1/2, then 1/3, then 1/4, and then it proceeds as you would expect from there. So yeah, it's a technical point, but I did want to mention it. So that's the sequence, and the center point is 3. Okay. Now, is the sequence non-zero for all n eventually? Right? That's all I mean by past some point. Is the sequence is eventually non-zero? Okay, yeah, certainly. It's 0 at the start, but from the second term all the way out, it's going to be non-zero. So the formula above is still valid. So let's just go ahead and compute the radius of convergence. And obviously, the general term here is just going to be yeah. So the nth term divided by the n plus 1th term. So the nth term is going to be 1 over n. The n plus 1th term is going to be 1 over n plus 1. Here everything is positive, so the absolute values don't have anything to do. Dividing fractions is the same as multiplying by reciprocals. Like so. So this is just n plus 1 over n. So what is this limit? Well, it's just 1. Okay, so the radius of convergence is 1. So that's not 0, that's not infinity. So the conclusion in this case is that the series converges if x is inside this interval and diverges otherwise. But then we also have to check the endpoints. So a minus r, comma, a plus r, which in this case, a is equal to 3. So that's 3 minus 1, comma, 3 plus 1. So that's 2, comma, 4. But now we need to check the endpoints. We need to check x equals 2 and x equals 4. So, checking the left endpoint, x equals 2, what do? Well, we literally just plug in x equals 2 and look at the resulting series. And now we use any one of our multitude of tests to see what happens. Right, so you literally just plug in x equals 2. So 2 minus 3 is negative 1. Okay, so looks like we have an alternating harmonic series, and we know that this guy converges by the alternating series test. I hope that you can go through the details of that in your head. I mean, 1 over n, certainly that's positive, certainly that's decreasing, certainly that goes to 0, so it's fine. Not to mention, I actually came up with a proof of this, which was geometric, but whatever. Alternating series test also works. So it converges at the left endpoint. What about x equals 4? So 4 minus 3 is 1. So 1 to the power n is just 1. Uh-huh. So that's the harmonic series. So this guy diverges. And I guess you could say by the p-series test if you want, but really you should just memorize that this guy diverges. That's a fact that's important in its own right, I think. So, altogether, the domain of the power series, also called the interval of convergence, is, so it converged at 2, so we need to put the brackets there, and it diverged at 4, so we put the parentheses. Okay, so that's it. So that's the domain. If x is outside that range, then it is guaranteed to diverge. So pretty cool. Okay, so here's a weird example, but it's important because this is an example that actually comes from physics. So the Bessel function of order 0. So I don't know if you've ever heard of Bessel functions before. Basically, they come up when you're looking at the physics of vibrating drum heads. So, actually, I mean, they come up even more generally than that. Just anytime you're looking at vibrations in a radially symmetric, like membrane. So you can imagine, of course, that would be ubiquitous in engineering situations, where if you're talking about a machine, and you want to analyze like the vibrations in a circular piece of metal on the machine, maybe you want to simulate those vibrations computationally. Well, if you want to do that, then you better believe Bessel functions are going to pop up. In particular, they show up as solutions to a particular class of differential equations. There's also the Bessel function of order 1, of order 2, of order 3. They just keep on going. And these are functions which can really only be written down as power series. There's no cleaner way to write them. So indeed, this by itself really should justify all of the work that we're putting into understanding series, because functions of this sort, functions that are only defined by way of series, are ubiquitous in science and in engineering. So it's very important that you have some understanding of how to handle them. So what we need to do here is we need to find the domain of the Bessel function. So notice this isn't exactly in the form that we want, because for a power series we need to have a power of n, but here we have a power of 2n. So only even powers are showing up here. So what does that mean for us? So let's write out the first few terms. So starting at n equals 0, we get, so this is all 1. When n equals 1, this becomes negative. X squared. Let me put the x squared here. I like putting them out front. I really don't like it when the book puts them in the numerator like this. I think that's... Ugh, I don't like it. Anyway. So when n is equal to 1, so this becomes 2 to the 2, so that's 4. 1 factorial is 1, so that's that. What would the next term be? So there's an alternator, so next it's going to be plus. So when n is equal to 2, that becomes 4. 2 times 2 is 4. 2 to the power 4 is 16. 2 factorial is 2. 2 squared is 4. So 16 times 4 is, 40 plus 24, so 64. Well, whatever. It's going to keep on going from there. But I want to draw your attention to, indeed, as I've already said, the fact that this guy is only looking at even powers. So what does that mean for the sequence? Well, the sequence has a term at every power, not just the even powers. So if only the even powers are showing up, then that means that C1 must be 0, C3 must be 0, C5 must be 0, and so on. So since only even powers show up, the odd terms of the sequence C sub n are 0. So the sequence is 1, 0, because the 1th term of the sequence is 0, and then negative 1/4, 0, and then 1 over 64, 0, and so on. So the general term is going to be what's given by this thing, but only if n is even. Yeah, only if n is even. Otherwise, it'll be 0. So let me indicate it like this, with zeros on either side, right? Also, these brackets are kind of shitty. Let me do the better ones. Hang on. There we go. The ones that actually fit the height. So what's the point that I'm trying to make here? The point that I'm trying to make here is that the sequence has infinitely many zeros in it. Uh-oh. For this formula to work, it has to be the case that the sequence is non-zero for all values past some point. Alas, that is not the case, because here it doesn't matter how far out we get, there's always going to be infinitely many zeros beyond. So unfortunately, this formula isn't going to work for this case. So what does that mean? That means we're just going to have to evaluate the convergence of this thing directly by using the ratio test. And what's the center point? Well, the center point is 0, so that's easy enough. So, since the sequence C sub n has infinitely many zeros in it, the formula for the radius of convergence won't work. Right? Because, I mean, you would just end up dividing by 0. So that's no good. So we need to apply the ratio test directly. By which I mean directly to the series, with x and n and everything in it. So it's going to be ugly, but it'll work. And incidentally, if you forget the formula for the ratio, or for the radius of convergence, then you could always just do the ratio test in the first place. The only reason I wrote out that formula up there is to save you some work. But you could always just do the ratio test and forget about everything else. Okay, so in the ratio test, it is the n plus 1th term over the nth term. So be careful here. In the ratio test, it's n plus 1 over n. In the radius of convergence, it's n over n plus 1. That is important. That's an important distinction. And, yeah, so we're looking at the entire thing, including x. Oh boy, so here we go. By the way, if you're going to go into engineering, well, I don't know. I don't know how bad it is, but my brief experience with it is that you can be working with some supremely ugly expressions. So proficiency in algebra is really a boon. Okay, so the n plus 1th term over the nth term, like so. I mean, I guess it would have been worse if we were in like the 60s or something, because, well, I don't know. Anyway, so these absolute values are going to kill the alternators, and everything else is... Well, actually, no, I can't say that everything else is positive, because we have this x here. X is a variable, so x may very well be positive. So the absolute values will kill the alternators, but we do still need to keep absolute values around the x terms. Anyway, so dividing fractions is the same as multiplying by reciprocals. So here I'm just distributing that. Hang on, I'm sorry. Oh, no, I had the right idea the first time. Yeah, because you only need to keep absolute values around the x's, because x is a variable, so you may very well want it to be negative. As for all of this crap, that's 2 to the 2n plus 2, and then n plus 1 factorial squared. Okay. So there's that. And then multiply by the reciprocal, so 2 to the 2n, n factorial squared over absolute values x to the 2n. And actually, you can pull the exponent out of the absolute values as well. Really only keep it around the x. That's fine. Okay. Alternators are gone. Absolute values are only around the x. Now let's start combining or grouping together like terms so that we can do a bunch of cancellation. So I will group the x terms together. Like so. I will group the power 2 terms together. Like so. And I will group the factorial terms together. Oh my god. Like so. Now we can see that a bunch of stuff is going to cancel. Whoops, there needs to be a 2n up here. Whoops, and this guy is called L, because this is the ratio test. Alrighty, so 2n absolute value x's are going to cancel, so we get absolute value x squared left over. And because this doesn't have an n in it, it's a constant, so we can actually pull that out of the limit. Here, 2n2's are going to cancel, so we're going to have a 2 squared on the bottom. So once again, that's a constant, so we can pull it out. Right, 2 squared is 4. Now, here, let's do our factorial trick. Because n plus 1 factorial is the same as n plus 1 times n factorial. So this is like so. And then I can take that square and distribute it. So this is n plus 1 squared, n factorial squared. Like so. And very convenient, because now these n factorial squareds are going to cancel. So we have 1 over n plus 1 squared left over. Okay, very nice. So now, this dude's going to go to 0. Huh. So this limit is 0. So what's the conclusion of the ratio test? Well, the ratio test tells us that if L is less than 1, then it's guaranteed to converge. Absolutely. And notice that it doesn't have anything to do with the value of x. X can be whatever we want. Multiplying it by 0 is still going to yield 0. So since L equals 0 is less than 1 for all values of x, we conclude that the series will converge absolutely for all values of x. That is, the interval of convergence is all real numbers. And the radius of convergence is infinity, if you want. Yeah, so that's really the observation. It's that this limit is going to be 0 regardless of the value of x. So that means I can plug in whatever x I want. The series is still going to converge absolutely. So that means the Bessel function is defined on all real numbers. And that's very convenient, since the Bessel function is very useful. Okay. So yeah, so the takeaway from that example is that if your sequence has holes in it, if you're only taking odd values or you're only taking even values, then this formula ain't going to work. So you're going to have to do the ratio test directly. And it's ugly, but you trust that it'll work out. All right, what about this dude? So in these next two examples, we can just compute the radius of convergence straight up. Because you can see there's an n here, there's an n here, so the starting point is 0, so everything is completely proper. So the sequence is... What am I doing? So the sequence is given by all this junk. And the starting point is 0. Or a center point, I should say. Okay, so is this dude ever going to have 0 in it? Nope. Nope, sure won't. It'll be alternating in sign, but the numerator is always going to be a positive exponential. The denominator is always going to be a square root. It's just getting bigger and bigger. So no, the sequence is not going to have infinitely many zeros in it. Yeah, so let's just go ahead and compute the radius of convergence. So now, because we're computing the radius, that is the reciprocal of the limit in the ratio test. So the nth term of the sequence is going to be all this. And the n plus 1th term is what we'll get when we replace n with n plus 1. Okay, so this dude here is going to be -1 to the power n, 3 to the power n. Similarly, an alternator is going to pop out here. Well, these absolute values are going to kill those alternators. And everything else is positive. So that's convenient. Oops. Multiply by the reciprocal. So n plus 1 plus 1 is n plus 2. 3 to the n plus 1. Okay, so I'm not going to bother rearranging it this time, because you can see 3 to the n on top, 3 to the n plus 1 on bottom. All of these are going to cancel except for 1, 3 on the bottom, which we can pull out. As for the rest of it, it's square root on top, square root on bottom. That means it's a big root. N plus 2 over n plus 1. Now, square root's continuous, so I can pull the limit underneath. The limit of this dude is 1, because the top and the bottom have the same degree, so it's 1 divided by 1. Square root of 1 is 1, so all this is 1, so it all just becomes 1/3. So that is the radius of convergence. So, what case does that correspond to? Not 0, not infinity. So it's this case here. It converges inside this interval. Yeah. So a minus r, comma, a plus r. Now in this case, a was 0, so that's just minus 1/3, positive 1/3, like so. Okay, and now we need to check the endpoints. So, first let's check the left endpoint. So plug in x equals negative 1/3. So here's the series. Like so. Oh, okay. So this is the same as right? This is the same as 1 over negative 3 to the power n. So how convenient. These two dudes are just going to cancel each other out. Negatives and all. So we are left over with this dude. Now, does this dude converge or diverge? Well, it is very similar to the series 1 over square root n. That is a p-series with p equals 1/2. 1/2 is smaller than 1, which means it's going to diverge. So I think we should probably do limit comparison test here. So compare it to the p-series, the divergent p-series. With p less than 1. Okay, so limit comparison test. So we are taking the limit of another ratio, but this time in quite a different context. So this divided by this. So just skipping a couple algebraic steps here. So this becomes 1, so square root of 1 is 1. So in the limit comparison test, all you want is for this limit to be a finite non-zero number. And indeed, that's the case. Yeah. diverges because we're comparing it to a dude which diverges. So that's the left endpoint. Now let's plug in the right endpoint. It's a lot of stuff, I know. So that's going to be exactly the same as this, but now this negative sign ain't here. So once again, 3 to the n, 3 to the n, those cancel, but we still have an alternator, which doesn't get canceled out in this case. So what about this dude? Well, this is going to converge by the alternating series test. So, the interval of convergence of the power series is, so it diverges at the left endpoint, but it converges at the right endpoint. So parentheses here, brackets here. Like so. And the radius of convergence is 1/3, but we know that already. Okay, one more example, but I mean, I think we know the drill by now. It's just a whole bunch of testing. So compute the radius of convergence and then proceed.